We're in this massive race to find better, cheaper ways to capture the sun's power. Well, according to one fascinating scientific paper, a single, really special material could be the secret ingredient we've been looking for. So let's dive in and break down what these researchers found.
I mean, just think about it for a second. What if solar cells could be rolled up, slapped onto curved surfaces, or even woven right into your clothes? That's the dream, right? But to get there, we've got to move beyond the tech we're using today. See, for decades, silicon has been the king of solar. And look, it's reliable, it gets the job done, but it's also rigid, it's heavy, and honestly, making it is a really complex and expensive process. Scientists are pretty sure we can do better, and that conviction has kicked off this global hunt for a new champion material. And that brings us to this amazing group of materials that's causing a huge buzz in the research community, the perovskites. Now, they're not one specific element, but a whole family of compounds that all share a really unique crystal structure.
So what in the world is a perovskite? Well, it's any material that follows this specific atomic recipe, this MbX3 formula. And it's this unique arrangement of atoms that makes it ridiculously good at turning light into electricity, a property that scientists call optoelectronic. And here it is. This is the atomic structure that makes perovskites so special. Just look at this beautiful, orderly little cube. You've got different atoms in very specific places, one right in the center, others at the corners, and more on the faces. This precise repeating pattern, this is the secret sauce behind its incredible properties. Okay, so the perovskite family is huge. Researchers couldn't study them all, so they pointed their supercomputers at one really promising member, cesium lead iodide, or CsPbI₃ for short. It's what's known as an all-inorganic candidate, which just means it doesn't contain carbon. And that's important because scientists think that might make it way more stable and durable in the long run.
So why all the focus on this one in particular? Well, the paper lays out some pretty compelling reasons. For starters, compared to silicon, it's way simpler and cheaper to make. It also has this natural, built-in ability to just soak up light. And because of that, it has incredible potential for super high efficiency. It really is a front-runner.
But hey, potential is one thing. Performance is something else entirely. So the researchers decided to put this material through a series of virtual tests, kind of like a computational gauntlet, to see if it really has what it takes to be used in real-world solar cells.
First up, the physicals. Is this stuff tough or is it fragile? I mean, you don't want a solar panel that's going to shatter if a hailstone hits it, right? You want something durable, and in a perfect world, something flexible.
To figure that out, the study calculated something called the bulk-to-shear modulus ratio. Now, that sounds super complicated, I know, but all we need to care about is the number they came up with, 2.13. So what on earth does that number actually mean? Well, it turns out material scientists have a pretty simple rule of thumb. If that ratio is below 1.75, the material is brittle, kind of like glass. It shatters. But if it's above 1.75, it's ductile, which means it can bend and stretch and deform without breaking.
And with a score of 2.13, our material doesn't just pass, it clears the bar with flying colors. This is huge. It means it's not brittle. It's a soft, ductile material. So test 1 is a definite pass. This is exactly what you want for those futuristic, flexible solar cells we were dreaming about.
Okay, so it's flexible. That's awesome. But it's pretty useless if it can't actually generate any power. So the next test digs into its electronic properties. How good is it at the most fundamental job of a solar cell, turning photons of light into a current of electrons? To get this, we have to talk about something called the band gap. The easiest way to think about it is like an energy price of admission. A photon of sunlight has to give an electron enough of an energy kick to jump over this gap. If the gap is too big, most sunlight can't afford the price. If it's too small, you just waste a ton of that energy as heat. There is a definite sweet spot. Now, this graph looks crazy complex, but don't worry, we only need to look at one spot, right there, at the R point. See that space between the lower and upper sets of lines? That's it. That's the band gap. And what's really important is that it's a direct band gap, which is basically the ideal setup for high efficiency. But how good is this computer simulation really? Well, get this. The study's calculation predicted a band gap of 1.88 electron volts. The actual real-world experimental value is 1.73. That is incredibly close. It's proof that the simulation is totally on the right track. And even better, both of those values are sitting right in the sweet spot for a great solar cell.
So, the verdict on test number 2?
It's another resounding pass. This material has a nearly perfect band gap. It is electronically tuned to be an incredibly efficient solar converter. Check.
All right, we are 2 for 2. It's flexible and has a fantastic band gap. But there is one final test. It doesn't matter how perfect your band gap is if the material doesn't actually absorb the sunlight in the first place. So how much of the solar spectrum can it actually capture?
The study's optical analysis makes this crystal clear. This material is an absolute powerhouse where it counts the most. It just soaks up visible light, all the colors we can see. And it keeps on absorbing well into the high-energy ultraviolet range. And that's where the sun's most powerful rays are.
And that is a hat trick. The third and final test is a pass. This material is an excellent absorber of the most energy-rich parts of sunlight. You couldn't ask for much better.
So after running the gauntlet of physical, electronic, and optical tests, what is the final verdict from this incredibly deep simulation? Does this stuff have what it takes?
The report card is, frankly, glowing. Physically, it's ductile and flexible. Check. Electronically, it has an ideal direct band gap. Check. And optically, it has excellent light absorption right where you want it. Check. It ticks all the major boxes for a next-generation solar material.
The authors of the study really say it all right in their conclusion. They describe a material that is pretty much perfectly suited for use in optical and electronic devices, which is, of course, a scientific way of saying things like solar cells.
This kind of study, one that starts from the absolute basic laws of physics, gives us an incredible preview of what's possible. By simulating materials at the atomic level, we can identify potential superstars like this one before we even spend a dime making them in a lab. It just makes you wonder, what other breakthroughs are just sitting there, waiting to be calculated into existence?